Hello, everyone, and welcome to Handmade Hero, the show where we code a complete game live on stream. Yesterday, we tested out a potential method for doing sorting, but don't think it's going to work. We're just kind of playing with some suggestions. So I think I'm going to go ahead and do what we had originally planned to do, which is just to do a full graph sort. Because, well, honestly, I don't know that there's that much of a reason not to. It seems like a totally legitimate thing to do, and, it's, you know, it's worth having some graph code in our game, probably. We'll probably have more of it. Getting a little used to writing some graph-based code doesn't seem like a bad idea, because I'm sure we'll have to do a little bit more of that when we do world generation, possibly pathfinding, and things like that. So graphs are a pretty common thing to want to be able to work with, and we really haven't had a lot of a cause to use them yet. So it seems like it's a totally reasonable thing to do here, to go ahead and take a look at that. So I'm going to go ahead and get started here. It is day 304, so you're going to want to unpack day 303's source code if you're trying to follow along with me at home, because that is what I'm starting with today. So let's go ahead and get our project up here. Handmade. There we go. And let's open up the sort. So we sort of did this alternative version of the merge sort here. We determined, and actually this was thanks to an excellent diagram Pushu's made, there seems to be pretty clear cases where this won't work. So I think we have to just determine that this is not going to be something that we can use. And so, all of this code is basically not useful, right? This is code that's not going to be useful for us. So we need something else here. And what we need here is some kind of an algorithm that will sort these in terms of semantic sort by who overlaps who. And it'll just take sprites that overlap, it'll try to do sorting around those sprites, and sprites that don't overlap, it won't try to sort those sprites. So it's kind of a very localized, very semantic process. And hopefully that will get us to the point where we can sort of get that working smoothly, and then we'll be able to put in whatever kinds of operations we want, right? We'll be able to say, okay, we can now just make arbitrary rules about what goes in front of what, and then hopefully we'll have a nice clean way of always having those come out with the best possible sort given the constraints by just pushing them through our graph sorting routine. That's the hope anyway. So you can see here we had a build sprite graph function that we started sketching out. I don't know if you remember, this was about 3 weeks ago because I broke the microphone and we were off for 2 weeks. But before that, you can see we went in here and said, okay, we're going to go through all of the nodes pairwise, and we're going to see whether they intersect in screen area. And if they do intersect in screen area, we're going to use our isInFrontOf to add an edge between them, which now says, hey, there's this sprite has to go in front of this sprite, or vice versa, right? So if A is in front of B, then we're going to add an edge that says A is in front of B. If it goes the other way around, we're going to add an edge that says B is in front of A. Okay? So this is actually pretty reasonable pseudocode. It's actually almost real code. But we're going to want to do a bunch of stuff with it, and plus it's n squared, as you can see here. So we're also going to want to do some work there with spatial partitioning to make sure that we don't actually go n squared, because the number of sprites we have is pretty high, like 2,000 or 3,000. We don't want something going n squared on that. We would see that in our frame rate for sure. And well, I'm sure we'll implement it n squared first, and you will see it in the frame rate. You shouldn't have to take my word for it. So taking a look at this, what we need to do here is just go, okay, now that we have a graph after this piece of pseudocode runs, we're going to have the information that we need to do the sort, but we haven't actually done the sort yet. So the next thing we need to do is we need to just determine what should be drawn first, right? And so if you imagine, and I'll just pop over really quickly here, to Mr. Milton. Let's see, there we go. Here we are. Here we go. So if you think about what's going to happen here, and I suppose I should also title this graph sort. So if you think about what's going to happen here, we have sprites, and those sprites are going to be, you know, something like this. We're going to see that they overlap in screen space, and our rule is going to tell us, you know, this one has to come behind this one or whatever, right? Or more specifically, A comes in front of B, right? And so what we're going to do when we have all of these here, and I guess we should also maybe make one more. And so in this case, we kind of know, all right, this is going to produce a graph, and that graph is going to have 3 nodes in it, right? A, B, and C. And what we know is that every time we determine that something is in front of something else, we add an edge from the thing that's in front to the thing that's behind. So in this case, A is in front of B, and B is in front of C, right? So I'll state the obvious thing first, because if you haven't worked with graphs before, it's probably not that obvious. The obvious thing is, if we then wanted to draw these sprites such that we drew the furthest one back first, right? Well, if we knew that we didn't have cycles, and remember we talked about cycles. If we knew that we didn't have cycles, and cycles would be like if we had one from here to here, right? So if we don't have cycles, then what we can say about this graph traversal is that there's a really pretty straightforward ways of us determining who to draw first and who to draw last, and so on. All we have to do is pick any random sprite. It doesn't matter which one. We just pick a random sprite, and we follow its edges until we can't follow edges anymore, right? We just go do, do. And there's no edges out of this guy, so we know he is a backmost sprite, and we can draw him. We know there are no other requirements to his being drawn. So he can be drawn at any time as long as there are no edges coming out of him that say that there's someone else who's in front of him, right? That's just the definition of our edge. So if we wanted to draw all the sprites in back to front order, all we really have to do is just go, well, start with the first sprite, follow the edges until we can't follow them anymore, draw that sprite, right? Go back, follow any other edges we didn't follow out of that node all the way to the end, draw that, right? And just keep following all the paths until we can't follow any more paths. Once we've drawn all of those, we've completely drawn that connected subgraph. And a connected subgraph, which, if I haven't already stated it, is if there were more nodes over here. There's 2 connected subgraphs here, right? These guys are all connected, and these guys are connected, but they are not connected to each other, right? So each one of these is a subgraph. We could say like this was subgraph 0, you know, and this is subgraph 1, right? So once I do that, I know I've drawn everything in this connected subgraph, right? And so then all I have to do is just make sure there are no other subgraphs. Well, how do I do that? Well, it's pretty easy, again, and I don't know that this is the method we'll use, but you can imagine a pretty trivial way of doing this, which is every time we draw someone, we just mark them as having been drawn. So we mark this guy as having been drawn, mark this guy as having been drawn, mark this guy as having been drawn. Now we just go to the second sprite, and we do the same thing we did with the first sprite. But when we look at the first sprite, the second sprite rather, we see it's already been drawn, so we know we don't need to consider it. And we move on to the third sprite. It's already been drawn. Move on to the, the fourth sprite. This one hasn't been done yet. Redo the edge following drawing algorithm, which will draw this sprite and then this sprite. Move on to the fifth sprite. It's already been drawn, and we're done. So just by looping over all the sprites, following their edges to the end, and drawing them in that reverse order, we would be able to trivially take our graph and draw it back to front. Very, very simple. So the only thing that we really have to worry about is the case where we end up with a cycle, because there's nothing that says that we won't get cycles. And if we have a cycle, then we have a problem, because if A is supposed to be drawn in front of B, and B is supposed to be drawn in front of C, but C is supposed to be drawn in front of A, then we will have a circumstance where there is no actual correct draw order for these sprites. We've created an impossible scenario. But the problem is that could happen. In the world of games in 2.5D, where we're kind of fudging it and saying, well, we're just trying to take 2D artwork and make it look like it's sort of existing in 3D, but we really know it's actually 2D. We're making stuff up as we go along, and we're making rules up like this always has to be in front of this, and this always has to be in front of this, because that's what looks nicer, right? But what looks nicer doesn't necessarily produce a consistent ordering. So at some point, we will have to figure out a way to break these cycles when they occur. The first thing we could do is just arbitrarily break cycles. And the way we could do that is, again, by marking as we go. And if we ever hit something that's on our path again, we just consider that path over. That's a trivial cycle break. It just says ignore the first cycle that would cause the actual loop to occur. That's probably not the final one we'll want to use if we do find we have a lot of cycles. If we rarely, if ever, have a cycle, we may not care. But if we often have cycles due to our rules, we're probably going to want something that's more intelligent about what kind of an edge it added, and to prefer breaking edges of certain kinds that we think are less likely to produce incorrect sorts. Okay? So hopefully that all makes some sense for you. Since this is the first time we've worked on a graph algorithm on Handmade here, at least that I recall, I'm going to take this in simple steps so that everyone will be comfortable with it. So the first thing we're going to do is we're going to build the graph. And we've written sort of that pseudocode that's very obvious pseudocode, right? We've written the obvious pseudocode for it, but we're going to actually do the work of really building the graph structure. Okay? Then we are going to find cycles. So we're not going to do anything. We're not even going to try to draw with it. We're not going to do anything with this graph at all. We're just going to ask ourselves, can we detect where all the cycles actually are, right? And, you know, in so doing, maybe we can remove edges from the graph that have cycles. So, we could say a sub one of this is remove them, And then finally, we will actually do the step of drawing the graph in order. So that's basically what I'm going to do in series there, and that way, we'll take it one step. We won't try to do everything in kind of one pass. We'll sort of take it one step at a time, and you can sort of see how these sorts of algorithms progress, right? And I'm not going to use any fancy algorithms. I'm not going to use any fancy graph theory here. I'm literally just doing the most basic kind of graph work that at least that I ever do, which is to just tagging nodes. Right? So the whole way that we would be doing anything here is we're just putting a little marker in those nodes. And you'll see that's very often a simple way to approach graph problems that works for a surprising number of different ways you might want to traverse them. There is, however, a whole huge, big field of graph theory that has all kinds of algorithms in it. And so when we're done with this, we may find ourselves in a situation where we want to apply some heavier firepower. If that turns out to be the case, we will. But at first, I just want to show you the very, very basics of working with graphs, and we're not going to try and fit our algorithm into some other kind of category, right? Okay. So here we go. We know we have a list of sprite nodes, and so when we do this sort of A-B thing here, in fact, looks like we have a bug in our pseudocode. That should be bound A, bound B. And when we do add edge, we're passing A and B there. And so what we want to do here is we've got these sprite nodes, and we want to actually build out these sprite nodes. Now, the problem with this is, as you'll see, if we want our graph to be optimized for walking, which is what we're doing, like we're trying to get from one place to another, then we kind of need some quick way to get from a node to an edge, right? We need some way of doing that. So probably we're going to need our sprite node to keep that in mind. Now, I don't know if we want indices here or not. I'm guessing that we might not. I'm not 100% sure. But if we take a look at what we've got for sprite bound, or what is it? Where is that guy? Yeah, here it is. So we take a look at what we have for sort sprite bound here, right? You can see we have like the sort key, and then we have the index. And the index is the thing we're trying to draw, and then we have the sort key, which is the thing that tells us how we're supposed to sort this thing. And what I would say is we don't really need a node structure per se, because we can just use those nodes that we have. We don't need to create new ones. We could just use those sort entries that we have. So really what we need to do is just kind of import this stuff here into what we've got, right? So I think we want to come out here and say, okay, if what we need for our sort key is the screen area and then these other bounds here or whatever, then that's what a sprite bound is now. And then inside our sort sprite bound, this is where we're going to sort of have this edge concept here. And I don't know that we need indices for the edges. It seems like we could probably use pointers, but I don't really know which one of those is going to be more efficient. For now, I guess we can just use indices because we will be able to look up directly, so that's probably fine. But what I do want to do is inside the sort sprite bound in here, I'm just going to chain these edges together. So I'm just going to make it so that we have a next edge structure, and then in here we just have a first edge structure. So now, when we're doing our sprite sorting, we know that we have the sort key as well as the edge list here, and so then every time we want to add something to it, we can just go ahead and use those edge structures. Okay. So let's go ahead and start to make that happen. Let's actually make these work. I'm going to move this up above here. So here's our sort entries function. And so in sort entries, we'd assume we would be calling the build sprite graph. You can see us calling merge sort with these two pieces of information. And so if I come in here and I say, okay, let's build the sprite graph. Here's the count. Here's the entries. And we no longer have this input nodes and input node count situation, although I guess I could just do it this way. All right. So assuming that we have some input, we'll go through them. For each pair, we will check to see whether they intersect. And sprite node is not what it is. It's called sort sprite bound now, because that's what it was. And we grab out whichever ones we're talking about here. We check to see if they intersect. And I believe this is technically a sort key. Although I guess no, it's not, now that I think about it. It's not really part of the sort key. That's not true. It really is just part of the check to see whether we want to sort things. So technically it probably should be in there. Okay. So then we check whether or not they intersect. Assuming that they do intersect, we then go ahead and sort their sprite bounds. And I guess we're doing, this is not really, I don't know that we really want to do this way. So I'm going to go ahead and say, let's do this. Right? And then our add edge stuff is correct. So since we add an edge every time, I don't know that I need to do this kind of a switch statement sort of a thing. So I think we could say something more like if is in front of. I think we could just swap the two, right? We could just say like swap A and B. Does that make sense? And I guess I don't even need to swap them. I can just swap their pointers, right? So I can just say like, okay, now we know that if A is in front of B, and I guess to make it easy on ourselves, maybe we'll say, well, okay, I'll do it this way. We'll just say that if A is in front of B, we'll switch it. Seems weird. Let's keep A in front of B. So if B is in front of A, we swap them. So we know A is always in front of B. Now, one thing that we could do, and I'll put a to-do here, is I don't know what we want to do if the sort keys are equivalent. I guess to tell you the truth, we couldn't not add an edge. So we still have to add an edge because otherwise you'd end up with the graph wouldn't work properly, I don't think. I don't really know. That we'd have to think about. I'm not sure about that one. But anyway, at this point, we know that we've kind of got an edge from A to B because we've swapped them if that wasn't the case, right? All right. So how do I add an edge from A to B? And I suppose, actually, now I think about it, since the edges are, I really only need to sort the node index, I think, right? I think I can really just do this. Right? Because I actually am only going to use this particular piece of information. So I don't know that I really need to swap A and B in this particular case. But, so let's take a look here. So now I need to add an edge. And so, oops. And so if I take a look at what our edge structure is here, right? I want to add one of these. So I need to do some kind of a thing where I'm going to have storage space for a sprite edge. So a sprite edge needs to happen here. And then once I have the sprite edge, I need some stuff. I need to know what is the next edge going to be. I need to know what's the front part of the edge and what's the behind part of the edge, right? And so in this case, I know that front and behind, I know that A is in front, and I know that, that B is behind, yes? So the only thing that I need to know is who the next edge is going to be. Well, what I said was I want to chain, and I should probably label these a little more specifically. So for a particular edge, what I want is the first edge with me, with whichever sprite we're talking about here, whichever sprite bound this is. I want the first edge with me as the front, right? Because I'm not going to point to edges that have me behind, because I want to traverse from something that's in front to something that's behind. I never need to go the other way, right? I never need to walk backwards. I only need to walk forwards. And so, or I shouldn't say forwards. I always want to walk from the frontmost sprites to the backmost sprites because we're drawing back to front. And we'd swap that if we wanted to draw the other order, right? Okay. So I want the first edge with me as front, and then this would be next edge with same front, right? With the same front value. Well, that's not exactly true. It's the next edge. Yeah, no, that's right. It's the next edge whose front index is the same, right? Because in the case where I have something like this, I'm going to want to walk through all of these, right? So I'm going to want to do this, and then this, and then this, and then this. So I want to know all of the edges that come out of a front node towards all the other nodes that they're marked as being in front of, right? Okay. So when I push an edge on, since I don't care about the order of edges, what I want to do now is I just want to know who node A is. Right? So I basically want to know my front node is input nodes plus node index A. And so my front node has a first edge with me as front. And I want to go ahead and take that and put it as chain it onto the end of my next. And this is, again, just a singly linked list. I'm just going to say, now make the edge that we just made be part of it, right? So here we fill in the data. Here we add it to the list. And now we've created basically our graph, right? That's all we really need for our graph. Here's all the edges now. We can walk them if we want to. That's all we need. Okay. So if this builds the sprite graph, then the next question is, well, okay, how would we actually iterate the sprite graph? And so if I do that, let's do the walk sprite graph here. And remember that all we really want to do, like I said here, is we just want to find the cycles. So what I want to do is say, okay, we pass the exact same piece of information. We just assume that it's been built already. Let's get out from behind my head. So we assume that we've already built the sprite graph, and now we have to walk the sprite graph. Like I said before, all we're going to do is we're just going to go over each individual one like I was planning to before. Exact same thing we did. Only this time we're going to go over all of them because we're not doing any kind of pairwise stuff. So we're not doing any kind of an n-squared comparison. You know what? We need to like get some more room. Here we go. All right. So if we're going to walk the sprite graph, we need to start at a node. And presumably what we want to do here is probably do this recursively at first. And we might not want to do recursively eventually because usually recursive is slower than not. And since this might be performance oriented thing, maybe not. I don't know. We'll see. Probably it's the part where we're trying to figure out who. It's this n-squared loop that's the one that we're probably going to have to concentrate on. So actually, to be honest with you, I don't think this part will really be that big of a deal, but we'll find out. All right. So anyway, I have to walk the sprite graph. I'm going to do that recursively at first. So I'm going to do recursive front to back. And all I need to pass here is I'm just going to pass the input node array and the one we're currently at. Right? So what I want to do here is I want to follow all the edges recursively of this thing and kind of fan outwards. So again, we've set it up when we built the graph so that the chains are easy to follow in this order. So I can do a sprite edge, and I can say, well, start with ats, first edge with me as front. As long as there is an edge, follow that chain, right? Just follow that chain through. And as we follow that chain, each time we walk one, we are then going to be in a position to actually do something with it. What do we want to do with it? Well, we want to call recursive back to front again, right? So we're going to, again, pass the input node array down through it. And actually, you know what? I could put that here as well. There we go. Input nodes, node index A. And what we could do here is note that when we do this recursive, typically we're going to be passing the index actually, because that's what the person starts with. So what I could do is I could just say, well, let's actually just do input nodes plus index. Right? That way we don't have to do it here, and we don't have to do it here either. We just pass edge back. Right? And we could also assert here that edge front equals at index. So make sure that we legitimately have built the graph correctly so that we don't have edges linked off somebody who really wasn't the edge, wasn't the starting node. So you can see us what we're doing here, right? We pick out the node that we're on from our array of nodes. We iterate over all its edge chain, and for each one we dispatch a recursive call for front to back. And that's it, right? That's absolutely it. So now we could actually make this stuff happen. Of course, we've got some stuff that we haven't done yet that would need to happen in order for this to actually do anything useful, but you can sort of see how it's about to happen, right? It would look like this. Count entries, and then like this. So there we have that. And now what we need to do as well is actually do some work in here, right? As it is right now, we just crawl the entire graph. But if there was a cycle, we'd loop forever, right? We would just keep on looping and looping and looping and looping. And since it's a recursive function, eventually it would run out of stack space and crash, right? It would just go to the end and it would just go until it ran out of stack space for the thread and crash. So what we want to do in here is actually do some work, right? We now need to actually do some work in here, and so that we can have a termination criteria on the case where it cycles. So let's take a look at what we recorded here for sprite bound and sprite edge. Here they are. Now we probably don't really need to mark the edges with anything at the moment because it's the nodes we care about cycling, right? So what we can do here is we can set something up where we just say flags. That gives us something to mark. And maybe we can call this a sprite flag. right? And so we've got, you know, sprite, in this case, visited, and sprite drawn might be examples of stuff we probably want to know. And so now we know that as we walk these guys, and we could clear those here if we wanted to as well, although we could also clear them elsewhere, so I'm not sure really how we want that to work exactly. But we could, for example, assert that they're clear as we're building. So while we kind of come through here, we could do something where we said like, oh, yeah, you know, as we come through here, You know what I just realized? This is not going to work because this part needs to keep this index. So sad, really. How about this? So in that case, we've got the front index and the back index, and then if it turns out that they're in the wrong order, so the B is actually the one in front, then we could swap the front index and the back index. Like so. And then here we just say like, okay, we know that this is the front index, this is the back index, and there's no more A and B, right? Better? I think so. So anyway, when we come through here, when we grab out A, we could also sort of hoist that up here, right? Because this A is going to be the same for the entire time. And so when we grab out A there, what we could also do is just assert that A's, what was that thing? Flags are 0, right? That seems pretty straightforward. Okay, so all that being good, what we now need to do is when we do the actual walking of the sprite, we know when we do recursive back to front, when we do this call, we pull out what the sprite is. What we can do here is say, well, okay, if the flags that we're looking at here, if these flags are set so that it looks like we visited this guy, then we wouldn't want to do this loop, right? If we've already been here, if that makes sense. And of course, when we go in here, we're going to have to set the flag. But this is of critical importance. The question is, where do we set the flag? Because we could set the flag in two different places. We could set the flag right here, or we could set the flag right here. And which one do we want to do? Sometimes it doesn't matter. In this case, it does. Why does it matter? Well, the recursive call is happening here, right? So if we set the flag down here, it might not do us any good, right? Because this recursion could just go ahead and do its little loop, and nobody ever gets marked as visited, so this will never actually happen. So we have to make sure we mark it as visited first, so that if this recursion path happens to hit the sprite again, it will stop. Right? So that's that, right? And so this is a simple one of just making sure that we never sort of get into an infinite loop while we are looping. Now the problem here is, at least thus far, we don't actually know. We don't really know much about cycles. In fact, I guess I might have almost. I guess I was perhaps not thinking ahead enough when I wrote these down, because actually what we just did is a draw graph in order algorithm. This would do graph drawing in order, but without intelligent breaking of cycles. So really this, now I think about it, is a little more advanced. I need an ID for my recursion to detect the cycles, and I don't need that for what I'm doing right now. So I guess really this is the simpler one. And that one's going to be a little more complicated potentially, but oops. So anyway, hopefully you can see how this works. As we go, we're just kind of leaving a little mark that says we visited so that we don't ever go and process that node again. So now, if we wanted to, we could go ahead and do work here. Right? This is where we would actually draw something, if that makes sense. So, you know, that's all there is to it. Not a whole lot else. So if we wanted to, we could actually go ahead and do that now, I suppose. So we could do the walk sprite graph. And what we need to do here is we need to have some place to put, you know, we need to take those sorted entries that we will have. Let's put it this way. We need to take our graph traversal, and since the graph traversal will be figuring out what the order is that we should draw things, we need a place to sort of output that data to, right? So I have to add to my recursive back to front, I need to add some sort of a printout here, like some output pointer, right, if that makes sense. So we need something like sort sprite bound, you know, out, right? But I don't want to pass it that way, and the reason I don't want to pass it that way is because I need to be able to modify that all the way back and forth on the chain. So I can't just pass a pointer, because a pointer gets passed by value, and I need the pointer to essentially be passed by reference so that I can update the pointer as it moves. And so what I'm going to do here is I'm going to do like a graph walk, just a sort of a context, which I can put in both the input nodes, if I want to, and the sorted output, right? And in this case, there's some interesting, there's a little bit of reason why we probably want to modify our routine here, right? Because if this is the sort information, I don't actually need to report back that sort information because it's way too much, right? I don't need to write back the sprite bounds or copy instances. All I need is an index list at the end. And so probably what we would want to do here when we do sort entries is we would probably, now that we're going from a large sort structure that has a bunch of information necessary for sorting down to just the draw order list, what we want to do is, you know, is have an output here. You know what I'm saying? So that we can write those things in there. And then that is what we would eventually want to pass. So when we come up through here, we have our out index list. We're going to want to write into that as we go. And so then I'm just going to say, all right, let's pass that sort graph walk down here. And then in this case, oops. In this case, we just say, okay, the input nodes of the walk, there we go. And then when we want to actually do something, well, the thing that we're going to do here is say, okay, the walk has an out index. That out index is going to be this one that we're on. Right? So that's actually the entire routine. I know it may seem a little surprising if you've never worked with graph stuff before, but that's basically all we're going to need for this simple in-order draw. Because all we do, like I said, is just chase it, and then as we unwind the stack, right, this recursive thing, as we return, each one of those guys just pushes C on, then B on, then A on. It just adds them to that draw order. And so when we're done, we just have the order walk that says only people who had no edges coming out of them or who had cycles are going to get drawn first, and then, you know, everyone after them in an advancing front that comes closer. And that's it. Now, unfortunately, we can't just run it because we have a bunch of dependencies that we haven't satisfied yet, right? There's a number of things that we haven't actually done. We expanded our conceptualization of what's happening to include an index list that gets written out. We haven't done anything with that yet. We also haven't done anything to address the situation with needing to use sort of push memory, although we do have temp memory, so we should be able to actually do that relatively easily, although we have to make sure that we size that temp memory appropriately, which is probably easier said than done in this case. And then we also have the problem of not actually ever filling out the structures that we actually need, because where is it here? Here it is. we've got this rectangles intersect situation happening. Well, nobody ever actually made any screen area. No one ever actually computed that for our sprites, as far as I know. So we're comparing fields that nobody ever filled out. And so before this is going to work at all, we also have to go upstream and make sure somebody actually writes down the screen area of the sprites. Hopefully that makes some sense. All right, so otherwise, I think we're in relatively good shape. So let's go ahead and get this compiling. Sprite edge, yeah, we don't have any way of doing that stuff just yet. That is what I'm going to have to do later. This got changed, its name, to that. And what have we got here? Sprite edge, illegal use of this type. I know that one. Sort graph walk undeclared identifier. It is sprite graph walk. There we go. Input nodes is an undeclared identifier. That is true, and that is actually not what you're supposed to pass. You're supposed to pass the walk there. In this case, we need that walk. So here is the sprite graph walk. And in this case, I want the walk input nodes to be input nodes. Walk out index equals out index list. What did I call that? Probably should be array. It's not really a list, is it? I mean, it's just an array. And so now when we call this, we got to pass that down. Okay. So yeah, I think we've got most of the stuff we want. Is it behind? There we go. Recursive back to front, still passing input nodes, not what we want. We want that. What else we got? Sprite edge. Okay, so I think we're done. So I think now all we have to do is actually clean up the sort of surrounding code and figure out how we're going to get ourselves some reasonable temp memory here. So I feel like in this case, do we have memory arenas support in here? We do. So if we want to, we could go ahead and have a memory arena, which I think is what we want, because we already have all the code for making these things work. So I think we want to do something like this, right? Yeah. And so now, since we're doing all of that, and we're going to call sort entries, I think instead of passing sort memory, we're just going to pass a memory arena here. And that way, when we do the build sprite graph, we can pass that temp arena to use. And that way, we know that we're going through something a little safer that's at least going to warn us if we screw up and, you know, all that stuff. All that good stuff. So I guess we do a push struct here. Is that what we called that? Yeah. So that all seems pretty good. The problem, of course, is when we come through here, we probably don't have the push stuff defined in the platform layer, I guess, which of course is actually including some of this sort stuff. And I don't know what we want to do about that. One problem, I mean, my thinking here is that I don't know that we want this code to keep running inside the platform layer. It doesn't really make any sense that it was down in there. You know, we move the renderer in there, but it ends up just being duplicated code. So what I think we want to do is hoist this up a little bit, and instead, when we do our render group stuff, I think what we want to do is call the sort before we actually ever finalize that stuff. And I don't know that we have a good place to do that. You know, part of the problem is just that we don't... Part of the problem is that we made concessions to make our debug stuff all flow through the same pipe. And in doing so, we ended up in a situation, which is not necessarily bad, but it is the case that, you know, I guess I probably should illustrate it in here. If we go down and look at how stuff finalizes, you can see that when we get down to the code that actually needs to sort of produce the final rendering information, here, here is where it is, right? And so the problem is, what we actually would want to do is we would want to do that before we ever did our debug, like before we ever got out of the platform specific code. So we'd really want that to happen, more like up, I don't know, where is a good place for that? We'd want that to be here, right? Where we do game update and render, we'd want to sort in here. But we can't sort in there at the moment because we have the debug system come in and it does it. And so we would need yet another thing at the end that calls back into the platform layer to do that sorting. So what I think is possibly the better way to go with this is to make that sorting happen in pieces that don't interfere with each other, right? Meaning, instead of having it so that you plow everything into the render list, and then you have, at the end, someone who sorts everything together, including all the stuff from the debug system, I'm thinking that the smarter thing to do would be that sort is actually inside the render, like when you produce a section of the render code, so that when the game produces its stuff, that's sorted, and then the debug system produces its, and that doesn't really even have to be sorted, potentially. We could make it so that the debug system just always draws an order or does something else. Who knows? Or the debug system also calls the sorter. Either way, I don't care, but I think that's what we want, right? So I think what we want to have happen is we want that sort to happen in a different place. Make sense? So yeah. So okay. So that's what we would like to do. Unfortunately, all this stuff is not going to happen in the next 10 minutes necessarily, which I think is how much time we've got. But we can do a bunch more stuff with it, right? We can get ourselves closer so that maybe tomorrow we could finish it up and start debugging. All right. So let's start with some obvious stuff. Let's go to render group. So here's how the render group works currently. Where are you, push entry? Push render element. So you can see how this works, right? You remember we push at the beginning and the end. And at the end, we push sort entries, right? And they kind of stack down in there. That's where this stuff is, right? So we know that we've got a bunch of sort entries, and we know that those sort entries exist at the end of the list. So what we should be able to do is we should be able to sort those sort of individually, right? Meaning, if what's currently happening is a relatively straightforward process of, okay, here is the element data, and here is the sort data. We've filled up this buffer, and now all we really need to do is replace this sort data with the actual order we want to draw things in, right? But we can do that at any time. There's no reason we have to do that, there's no reason we have to wait, I guess is what I'm saying. Because here's like the game sort data, right? And here's the debug sort data. And there's no reason we have to wait on those, right? We can produce multiple ones of these and then run them, right? That's well within our ability to do. And so that seems like a reasonable idea to me. The other thing we could do, and I'll have to think about this, but the other thing we could do is not actually... we could think of these as being more separate. So we could have like 2 push buffers or something where we push in elements and then sort data. And then sort data, the element buffer just stores everything that we're going to need to draw. These kind of get baked down into lists, or I should say arrays, of indices back into the element data. And those arrays of indices are what we then pass down to draw. And we have one for the game, and one for the debug. And so I'm not sure how I want this to go. Nah. I have to think about that a little bit. It would seem to me that either way we're going to need some sort of additional information here because, for example, if you have multiple people who all pushed into this buffer and you're saying we're not going to sort these guys against each other, then you end up in a circumstance certainly where you'd at least have to say that this stuff gets drawn on top of this stuff, right? Because the debug information has to be drawn on top of the game. And so if they didn't get sorted together, you would end up in that situation. I'm not sure what I want to do about that. I would say that the other thing, and it's not really obvious to me why we didn't already do this, is I'm not sure why we don't draw in 2 passes. Like, the other way to do this is we just draw the game data once and the debug data in the second pass. And maybe the reason we didn't do that is because we wanted to be able to integrate debug elements into the game so that they sort inside. I don't know that that makes a whole lot of sense as a goal, though. So, do you see kind of what I'm saying there, where I feel like we could do something where we just do a begin and end pair and then a begin and end pair in a way that's cleaner than that, So let me just kind of make that a little bit more directly illustrative for you. So I guess what I'm saying here is, if you take a look at what happens in the Win32 stuff, you can see that we have let's go ahead and drop the render commands. You can see here that we make our render commands, right? And we come through here and we give the game the ability to add to those render commands. There's nothing to stop us from right here issuing those render commands, right? And then creating another one of these that we then have occur down here, right? Where is it? Right here. So I don't know. Let's take a look inside. I would like to know what is the clip memory used for? I'm just curious. Like, where do we actually use clip memory? Because we pass clip memory when we call Win32 display buffer in window. Like, there's clip memory, and we do linearize clip recs there. So, okay, so we're just pulling stuff out of we're just trying to make a linear version of the clip recs. So that is also something that could have been done by the other code, right? So there's just a lot of leakage here where we're getting stuff out into the platform layer that doesn't really need to be there, and it's just because it's more convenient to do it that way at the time, which is fine. But like I said, this is kind of a situation where I'm thinking to myself, do I want to take a step here and smooth that out where that's actually done in the platform independent layer, and so that we have the sort and the linearize happen there, and then the game code is only responsible for doing the basic operation of iterating over the draw list. And I think I do. I think I do. So I think what I'm going to do is I'm going to not try to do that right now, because I think that's going to be too much, probably, for right now. So what I'm going to do instead is I'm going to probably go ahead and leave this a little bit gimped at the moment. Let's see here. Push. Oops. Where is my push? There it is. So I'm going to go ahead and do my make sure that works. And then when we call sort entries here, I'll just pass 0. And this will just be well, I guess let's actually move this into platform specific. There. In fact, you know what I could do? Just do that. So now I think actually we'd still run, and our entries just won't be sorted. So there you go. All right, so we won't crash. So I think I'm going to end it there, and then what I'm going to do tomorrow is I'm going to move that stuff inside, and we'll keep the sorting inside. And then we will go ahead and finish up our graph stuff. And yeah, and that I think will be good. So let's go ahead and go to the Q&A, in case anyone has any. Questions? Does anyone have questions? Was enabled. Did you discuss why you are using recursion and any concerns with stack overflows? Yes, actually, when I typed that in, I said we probably won't use recursion, actually. So the recursion is just there because it's the easiest one to see first. But I don't know that I'm necessarily concerned with stack overflow. I'm more concerned about the performance overhead, because I've had bad experiences in the past with relying on recursive functions. They take longer than you'd think they would. Or maybe I shouldn't say that. They take as long as you would think. There's an extra function call every essentially iteration of a loop, which is just a ton of wasted work, right? And so I would say that my inclination is that there will probably be enough fussing around in here that we will not want to use a recursive function for traversing. Brian Wag. Working with graphs can be difficult. Do you have any techniques for debugging them other than observing screen renders, or is that mostly sufficient? So I guess what I would say is, in this case, what we're doing is pretty straightforward. So it's possible that we'll be able to do it with just observing screen renders. But I would say no, in general, that is not sufficient. So it might be sufficient this time around. I don't know that it would be sufficient most of the time. Certainly, I've had times when graph things are more complicated and it's not sufficient. And what I can say is there's typically two approaches there. One is you just make something that draws the graph yourself, so you can watch it. And the other one is that you dump to a data format and then feed it into a graph drawing tool. right? And so, you know, if we end up in having trouble debugging our graph stuff, we'll employ something like this, one of those techniques. If we don't, we won't. But yeah, I would say that it depends on what you're doing. The techniques that I'm contemplating using here aren't that complicated, so we might not ever run into a circumstance complicated enough to warrant more advanced graph debugging techniques. But if you're doing complex things with graphs, you often can run into that for sure. And it is not, and you typically do need a visualization for that. Rome says, did we address the possibility for intersecting sprites? We won't allow intersecting sprites, so that's just considered not a thing, right? Meaning if sprites intersect, whatever happens, happens to them, as far as I'm concerned. Luminian, when I code, I use the mouse a lot. You seem to be using a lot of shortcuts to jump here and there. Could you tell me more about your shortcuts? Yeah, I think I documented them all on the 4Coder stream. I mean, basically, if you have pre-ordered Handmade Hero in the source code, inside the source code zips, they're actually all in there too. 4Coder Casey has them all. They're right here. Where is that? Here it is. So like these are all the shortcuts and what they're bound to. Do you know the dev Gary Newman? No, I don't think I do. Yeah, Sean, I'm sort of snooping the chat right now since there are no questions. I really wish Razer would not make you have an account. I wish the drivers were just on the stupid webpage and you could download them easily and all that sort of stuff. But yeah, I've been meaning to tweet at them about that because I really like their hardware. What's that shirt? This is a owl. It's a cool owl. It was given to me by my friend Matt Cornell. He's given me I only have 2 cool shirts, and this is one of them. And Matt actually gave me both of them. The other one is a blue shell from Mario Kart, but done in the style of a Da Vinci, like a Da Vinci Uber weapon sketch. All right, if there's no more Q colons, I will wind it down. I will wind it down. And you know what I should do too, since we have a little extra time here? I should download the new version of Milton. So maybe I'll do that as soon as I wrap up here. All right, thank you everyone for joining me for another episode of Handmade Hero. It's been a pleasure coding with you as always. If you would like to follow along at home, you can always pre-order the game on handmadehero.org. It comes with the source code even as we develop it. You can also go to our forum site, which has questions and answers and all kinds of good stuff like that. We have a Patreon page you can go to if you want to support the video series, a schedule bot you can go to if you want to know when we're going to be live, and an episode guide for trying to catch up on old parts of the series if you're coming in new. That's about it for today. I will be back here tomorrow at 8 p.m. Pacific Daylight Time. Hope to see you all here for that. Until then, have fun programming, and I'll see you guys on the internet. Take it easy, everyone.